Hi everyone, so welcome to the next instalment of our MIPS video series on physical AI. And this one I'm joined by Mayank Mangla. Hi Mayank, how are you?
Hi Mike, I'm good. How are you?
Excellent. Okay, so in the last episode, we basically had your colleague David Bell discussing some of the use cases which were related to physical AI in a sense perspective. Now I think you're going to talk about the think use cases, is that right?
Yes.
Okay, great. So first of all, in an ideal world, you'd be able to put like the data sensor resources into a robot or a car or so forth. But obviously there are constraints that stop that from happening, aren't they? So how do you sort of overcome that?
Yeah. When I think about AI, it's a very vast field, and there are data centers and there are edge processors. So the way I like to think about it is, a data center is where AI goes to school, and edge is where it goes to work. So you take a model, train it on a data center. It's very computational intensive, very memory, very power intensive. But when it's deployed on the edge, it needs to run on a battery powered device,
Yeah,
or on a car which has very tight thermal characteristics.
sure.
And because of that, an edge inference chip has to be designed with all those constraints in mind. So it needs to be very power efficient, it has to be cost efficient for AI to become democratized, and it has to be extremely low latency. So think about a
Yeah,
car which is driving on the highway and there is a pedestrian in front. It has to react faster than a human would react in that scenario,
yeah,
right? It does not have time to send the data to cloud, get the inference, and get back down. Similarly, in a factory, when a robot is moving and it sees a falling object, it has to go and grab it and stop the damage from happening in almost human thought latency.
mm,
So that's where so MIPS is focused on physical AI, and physical AI is the branch of AI which deals with working with the physical world, with the sensors. The sensors are the eyes and ears, and AI is the brain. So that's where the thing comes into picture. So
sure.
you get the real world physical input, the light, the sound, the vibration, and then the AI chip, the brain of the robot or brain of the car decides what to do with it, and
Mm,
then it again results into a physical action through an actuator or through a brake or through a steering wheel or through a robot trying to balance on its feet. So
yeah.
that's how I like to think about the whole AI universe.
But basically, as you say, that's taking the sense data, thinking about what needs to be done, and then moving that on to action, whether that's
Exactly.
responding by braking, making a maneuver in the case of a car. If it's a robot in a factory, it might be stopping or avoiding an obstacle or whatever. So obviously these
Exactly.
things quite often, or very often, are going to be safety critical. So they need to be done in very low latency. They
Absolutely.
need to be, sort of rapid reactions and so forth. Okay, so that's really important. So you touched on a couple of possible use cases there. Maybe you could give us a bit more elaboration on some of the use cases um, where MIPS is using this think side of the physical
Yeah.
AI sort of.
Yeah, so one of the classic examples of the sense, think, act, communicate stack is, think of a car,
Mhm.
a car which either is driving itself or is helping the driver drive and prevent accidents on the road. So the sensors on the car are typically cameras, radars, sometimes lidar, and those sensors are bringing real-time information into the central computer inside the vehicle. And then the car is moving very fast, so the time to react is in order of few milliseconds.
Mhm.
So in this use case, the car needs to sense in all the four directions, and this is where it performs better than humans, because humans can look only in the front, maybe on the side,
Yeah.
but the cameras mounted on the car can look all around the car, and that's where AI models like bird's eye view become very important. So bird's eye view is a paradigm where you collect feed from all the cameras around the car, you
Mhm.
combine them together, and you create a view of how a camera on the top of the car would look like. That's why it's
Yeah.
called bird's eye view. And the leading model in this world, in this segment, is BevFormer, which originated from a research paper, and a lot of companies have now have their own optimized flavors of BevFormer, and MIPS is also working on its optimized flavor. So what BevFormer is really a very interesting model. It is computationally quite intensive, and it is as the name suggests, it is based on transformers. So it is Bev, it is bird's eye view, and former comes from transformer. But it has a lot of convolutional layers onto it. In fact, the way to optimize it is to use a convolutional backbone and then use a transformer network, a vision transformer after that. So that makes it quite challenging. And a lot of NPUs which were designed only to handle convolutions can handle the first part very well, but the second part of BevFormer they cannot handle very well. And that's where MIPS is designing S8200, which can handle not only one AI model, but it's designed for universal on-device AI. So any kind of AI model, past, current, and even future, should is some designed for. So S8200 is designed to handle all of them efficiently. So it is designed with the software first paradigm in mind. So we look at the use cases, we look at the workloads, we do a simulation using our Atlas Explorer, and using that we realize what are the common bottlenecks, because sometimes it's not just enough to add lots of matrix multipliers. Sometimes the bottleneck happens in memory access, sometimes the bottleneck happens in vector processing, specifically with transformers. You get into a lot of softmax, layer non-point kind of operation, which shift the bottleneck to a most unsuspected place. And that's where, before we design the hardware, we want to run it through the workloads, and we want to make sure that we have identified all the bottlenecks. And then when it is deployed, the customers, the users, get the most return on their investment in terms of cost and power. So we talk about use case performance, not just TOPS, but the use case performance.
Because I guess you don't want to get so far down the line that you're taking it to a hardware stage and then find out that there's bottlenecks that you didn't anticipate, and then the whole thing is going to need reworking somehow to sort of mitigate those. Okay, that does, makes a lot of good sense. So, so that way you can uncover potential issues earlier down the line.
That's correct, because reworking hardware is very expensive.
Okay, so that's cool. So would there be VFormer then? That's, as you say, that's based on academic sort of studies, and then different companies have their own sort of variation of that then? Is that how it's... Okay.
Good.
And from a MIPS point of view then, you want to make sure that that's got the ability to deal with multiple workloads simultaneously. Is that what you're saying? Yeah. Okay.
Yes. So when someone is running a model on a car, it's not just one model. There are several things running in parallel.
Yeah.
So BevFormer is what you use for perception, but once perception gives you the model of the world, like what are the cars around you?
Yeah.
Are there any pedestrians in the path of the way? But once you build that environment model, the car has to decide what to do with it. And for that, there is something called drive policy, which also runs in parallel. So drive policy decides, based on the environment, what the car should do. Should it go faster? Should it slow down? Should it change lane to avoid the accident? So, and all those are AI-based techniques, and all of those are working in parallel. So that way, it becomes quite an interesting and quite a challenging problem from a whole system point of view.
Okay, right, okay. So you touched on, obviously, on the automotive one, and that's obviously a very important use case. How about sort of more like industrial automation? Are there some use cases you could describe for that as well?
Yeah, so industrial automation is a very fast growing field. By 2030, it is expected that US will be short of almost 2 million workers. Right. That creates the opportunity for a lot of automation, and robots are at the forefront of it.
Okay.
So robots are going to be deployed from factory, warehouses, to delivery, to autonomous mobile robot, even in home as personal assistants. And robots are going to get more and more smarter. So so far the robots which are working in factories follow a very guided path. So you have to draw the very clearly demarcated boundaries and they follow that. But as the technology gets smarter, robots will be able to handle more complex problems. And they will be able to interact with humans just as humans do. So, for example, if you give a command to a robot, go do, go get me a cup of coffee. Now that includes a multimodal AI. So robot
Yeah.
has to listen to the audio signal, interpret it as speech, run a language model to understand what the user is trying to say.
Yeah.
Based on that language model, it has to now decide what to do. And when in a sense, get that coffee cup, now vision comes into place. So it uses its cameras to get a sense of scene around you. It has to see, it has to understand what is the subject of the command. If it's a coffee cup, which coffee cup is, what does the coffee cup look like? So detecting it, identifying it, going it, and even grabbing it as a human touch. You don't want to grab it with too much force that the cup breaks, and you
Yeah.
don't want to handle it too softly that it falls. So that brings the actuation into the picture. So it's got everything. And that's where we talk about models which are not just vision, not just language, but it's a combination of several modalities. And the leading models today on that are called vision, language, action models. So
Okay.
where you use vision, you use language, which results into an action, and that completes the loop. So that's again where MIPS, sense, think, act, communicate all comes together to create a cohesive final product.
As you say, there's lots of different things. They're starting off just recognizing it as the audio being voice, being able to interpret that voice, then being able
Yep.
to sort of understand what the task involves, and then how to implement that in terms of identifying where there's a coffee cup, how to pick up the coffee cup, everything like that. So it is a very complex set of different stages that has to be.
Exactly.
Yeah.
Exactly.
So
Yep.
okay. And then, so how does open modular technology enable better AI implementation?
Yeah. Yeah. So before going into the open technology, let's see what is the current landscape. So there are GPUs and you know the leaders there. And GPUs are great for training, they're great for floating point performance.
Sure.
But what you need in edge inferencing low power is more fixed point performance. It's more not so much of training it. It's again inference, and there are a lot of ways to optimize it through quantization and other techniques. So GPUs are still quite commonly used, but they are not the best fit for the embedded edge inference.
Yeah.
Other option is you will see a lot of proprietary closed NPUs,
Hmm.
which also come very often with closed source software. So it's like a black box. It either works or it doesn't work. If it doesn't work, you go back to the vendor and you tell them, hey, I tried to run this model, it doesn't work. And the vendor would have given you a set of models which they have tested and productized, and they were great. But if customer wants to bring their own models, it becomes a very, very difficult task running it on those closed source and closed architecture. Similarly, those those NPUs are designed to handle a certain class of applications. And if a customer has its own variation upon the network, for example, BEF format.
Hmm.
When we take BEF format, as I said, every company, every car OEM will have its own flavor of it, and some of them will try to optimize it in a different way. But if the hardware doesn't support that optimization, to give an example, if somebody wants to do 4-bit quantization, there is no benefit of doing it if the hardware doesn't support 4-bit format.
Right.
And that's why there is a lot of creative liberty which gets squashed because the hardware doesn't support what the model designer wanted to do. That's where the open architecture and open software comes into the play. MIPS is following a RISC-V based approach. So RISC-V is an open architecture founding lots of member companies who all come together, discuss, debate what kind of data formats we need to support, what kind of instructions we need to support. So it's something where a lot of companies are coming together, a lot of brains, a lot of smart people on the planet coming together to define one architecture, which then is agreed upon by everyone. And so you basically, you don't have to do everything yourself. You leverage the ecosystem, both for hardware and for software. But at the same time, RISC-V also allows you to extend the instruction set. It allows you to add more, make the software more modular. Just to give an example, one of the challenges in handling transformers, whether it's language models or vision transformers, are some operations like softmax. And this was not a problem in convolutional networks. So all the NPUs which were designed till 2022, before ChatGPT came, they were all heavily biased towards convolutions. And now suddenly transformers came and everybody was surprised. And one of the challenges there is softmax. And very, very few NPUs today have support for that. But in RISC-V, if you had to do that, if you just add one or two custom instructions, and then you get hardware application with softmax. That's a huge performance bottleneck which gets solved by open architecture. Okay? Similarly, in software, we are following an MLIR based approach. A lot of traditional NPU vendors are using library based closed source software stack. And the problem with them is if the customer wants to even change one line of code, they have to go back to the vendor and then negotiate with them, and can take months to just get one line of code. But if they have the code, they can make the change themselves, and they don't have to change the entire stack. That's the advantage of being modular. So in Erie is a popular MLIR based stack. It structures the software stack in form of dialects. So you can just replace one dialect. Maybe you have your own optimization, or there's a third party who can provide you that plugin. So you can replace one dialect with a more optimized dialect, and suddenly you can get the performance for the model which you want. So that's one of the advantages which give you not only the best power and cost efficiency, but it also gives you fastest time to market.
Yeah. As you say, that gives them the freedom then to change what they want to without having the issues of having to go back to a specific vendor, and then sort of, and also then it's, you've got the ecosystem around it, so you've got the support of that. It's just going to be an easier sort of prospect for them to use, an open source model like RISC-V to do that. Okay, so that makes sense, and obviously MIPS is very strongly sort of supporting that, which makes sense. Let's talk specifically about the S8200, which I know is the main sort of core you've got for these think use cases. So in terms of how physical AI think use cases are going to be implemented, how is that device or that particular processor core going to be beneficial to engineers?
Yeah, so S8200 is NPU. NPU stands for a neural processing unit, which is designed grounds up for physical AI on the edge. Low latency, low power, low cost. It's not something which was designed for data centers and now force-fed into physical AI.
Yeah.
It's grounds up design.
This has been from the start specifically created for this. Yeah, okay.
Correct. Yeah. It's a software-first approach, so which means we look at the workloads, we look at the target segments, who is going to be the user, and how is the user going to use the product, what kind of workloads they're going to run, what kind of software they're going to run, how does it interact with the host processor. So it's designed with all that in mind. And that's where our goal is the number one goal is to increase ease of use. We've been in AI industry for a long time. We know that the hardest problem is actually the software, is to making sure that the customer, once they have the model, it is hard enough to get the right performance, right accuracy on the model. But once you've trained that model, we want to make sure that it runs on an S8200 out of the box. So the migration from, if you train it on a GPU, migration from GPU to S8200 should be as smooth, as fast as possible. Yeah. That's what engineers really care about. They want good documentation, they want open source, they want ability to add performance counters, use tools which help them predict the performance without actually deploying it on the hardware. And that's where S8200 comes packaged along with our Atlas Explorer, which is a hardware software co-design tool. So without building the hardware, without spending a lot of time coding your application, you can simulate it in Atlas Explorer, and you can say, I have this model, I have this hardware definition, this is the performance I'm going to get. And if the performance is not what you want, you can go back, either you can tweak your AI models, or you can change the hardware spec. So that way, engineers can take decisions more confidently, and they can maximize the chances of success.
Because they have a better idea what they can expect, and then they can act upon that. Okay, accordingly.
Correct.
Yeah. So in terms of what you expect to see in the physical AI domain in the next few years, what would be your predictions?
So my prediction is, now if you watch CNBC, you will see that data center build out gets all the media attention. But my prediction is that there will be a lot of growth in edge AI, which is a space doesn't get talked about enough.
Yeah.
But if you look at the privacy concerns, if you look at the data sovereignty concerns, you look at latency, look at cost and power, I mean, AI is an energy problem. So low power is going to be a big differentiator in AI. And that's where moving to edge and designing more and more efficient, power efficient chipset is going to be the key trend for the next 3 to 5 years. And that's where MIPS plays a pivotal role. So we bring highly power efficient IPs to the customers, and that is just one part of it. It will be meaningless if customers cannot write software on it, if they cannot build the products they want to build on it. So it's a combination of great power efficiency. It's a combination of universal on-device AI along with the software ease of use, which is going to play a pivotal role in getting AI in hands of masses, where all the cars are going to be much smarter than what they are. Robots are going to be much more pervasive, and AI is going to be pretty much everywhere. Just like you see, internet is now your light switches in the home have internet. So I do expect more and more devices to get more and more intelligent as we
Sure.
go.
Yeah. And obviously that is likely to happen. There's going to be much more intelligence at the edge across everything we do in normal everyday life, I guess. Just touching on one thing there, obviously MIPS from that point of view is you could deal with the sense side of it, you can deal with the think side of it, and then the act and the communicate side of it. So having that sort of portfolio of different IP solutions, that must be important as well, because you're not just sort of dealing with one part of it. You can support the whole implementation then, yeah?
Absolutely, that's right, yeah.
Okay. So that's key differentiator for you, I guess. That's great. Okay,
That's right.
Thanks, Mayank. It's been an absolute pleasure speaking to you. And yeah, thank you very much.
Thanks, Mike. Thank you.
Okay.
Thank you very much.
In the future.